In our previous video, we learnt about rational numbers. We saw that rational numbers were those numbers which could be expressed as a ratio of any two integers. That is, they could be expressed in the form a by b, where a and b both were integers. And even in the case of just integers, like say 120, they could also be expressed as a ratio of two integers, just that the denominator would be equal to 1, where 1 is also an integer. So all the numbers which we have learnt so far, natural numbers, whole numbers, fractions, integers, all of them fall under this category of rational numbers. Now, this problem was posed by Pythagoras, the famous mathematician and philosophist Pythagoras. Suppose there was a triangle, a right angled triangle of base 1 unit and height also 1 unit. What was the length of the diagonal, the hypotenuse, of this triangle? This was his question. Now, since this is a right angle triangle, let us recall whatever we know about right angle triangles, and let us recall the famous Pythagoras theorem, which says that if the base was A and the height of the triangle was B, or the two sides of the right angle triangle was A and B, then the hypotenuse C, the hypotenuse which is the line, the maximum length, the side of the triangle of maximum length opposite to the right angle would be equal to the sum of the squares of both the sides of the triangle would be equal to the square of the hypotenuse. This was the Pythagoras theorem. So applying that theorem here in this unit length triangle, can we find the hypotenuse? Yeah, we can surely. So the hypotenuse would be equal to, suppose you call it h, h would be equal to root of 1 square plus 1 square according to the Pythagoras theorem, which is h is equal to root of 1 plus 1, which is root 2. Now root 2 is of course a number, and since we only knew about rational numbers till now, people knew only the existence of rational numbers, and according to them all numbers which were available could be expressed as a by b, as a ratio of two integers a by b. So let us see if root 2 also fits into this category of a by b. So let's see if it lies in the collection of rational numbers. So we are assuming that root 2 is equal to root 2 is equal to a by b, and if consider any fraction, it can be expressed in different ways. A fraction half can be also written as 2 by 4, it can also be written as 4 by 8. Out of all these, we consider this to be the irreducible form of the fraction. That is, there are no common factors in both the numerator and the denominator. Whatever common factors were there initially have been divided, and half has been, 1 by 2 has been arrived at. This was divided by 4 by 4 and half has been, these are all equivalent fractions, and this is the irreducible form. But they all denote the same rational number or the same fraction, right? So let us consider the irreducible form of the rational number here. So we see that a and b do not have any common factors. If there was any common factor, it has been factored out, it has been divided, and a by b has been arrived at. So a by b do not have any common factors. So let me write that a and b are coprime. Coprime meaning they are factors, there are no common factors other than 1. So a by b are coprime numbers. So this being said, let us now explore. Root 2 is equal to a by b. Now root 2 is a little difficult to handle in calculation, so let's square both sides of the equation. So what do you get? You get 2 is equal to a square by b square, or in multiplying both sides by b square, we arrive at 2b square is equal to a square. Now b square is an integer. B is an integer. B is an integer, so b square is an integer. So 2 multiplied by b squared has to be even. So a squared is even. This implies that a squared is even. Now let's recall, if two even numbers are multiplied, even multiplied by even will give you a even product, right? The product would also be an even number. If two odd numbers are multiplied, odd into odd would give you a odd product. Now in this case, a squared is even, and it is a multiple of a. A multiplied by the same number a. So a multiplied by a is even, so the product is also even. A squared is even, so which means that a is even, right? If a squared is even, then a is also even. So if a is even, you can express a can be written as 2. That is, 2 can be factored out of a, because a is even. 2 has to be a factor of a. So if 2 is factored out, a can be expressed as 2 into k, where k is some constant. So a is equal to 2k. Now if a is equal to 2k, let us substitute a in this equation again. We have 2b squared is equal to a squared already. But we know that a is equal to 2k, so 2p squared is equal to 2k the whole square, which is 4k squared, or in short, b squared is equal to 2k squared, which once again implies that b squared is even. By the same logical argument which we did here, that it is k is an integer and 2 multiplied by k, so b squared is even, which again says that b is even. So now we have, out of all this manipulation, we have arrived at two things: a is even, b is even. But what have we considered here? We have considered the irreducible form of this rational number a by b. But here is a contradiction. It says both a and b are even. That is, 2 is a factor of both a and b. So this is a clear contradiction, isn't it? If you are not convinced by this reasoning, please see our video, Proof by Contradiction, which has been posted in this channel. You'd get more clarity. So let's proceed now. So what have we arrived at? We've arrived at that a and b have common factors, and that factor is 2. So our conclusion is root 2 cannot be a rational number, or root 2 cannot be expressed as a by b. It cannot be written in the form a by b, or root 2 does not fall in the rational number category. It does not lie in the collection of rational numbers which we had mentioned earlier. So in the same way, actually, we can prove that the square root of non-perfect squares, 2 is not a perfect square, right? Like suppose square root of 9, it is plus 3 or minus 3. So this is definitely a rational number. Whereas what is the square root of 7? It is a non-perfect square. There is this again cannot be expressed in the form a by b by the same argument which we have done here. By this same argument which we have done here, root 7 can also be not expressed as a by b, and root 10 also not expressed as rational number for that matter. So all square roots of non-perfect squares are found not to be rational. But do you think that these are all the numbers which are not rational? Meaning, are there more numbers which are not rational? Let's see one by one. First, let's see what were these numbers called. If they are not rational, what were these called? Now, rational numbers are all the other numbers, in fact. As we saw, natural numbers, whole numbers, integers, all of them were called rational numbers. But these irrational numbers were, this was the name, of course, because they are not rational, they were called irrational numbers. The numbers which were not rational which could not be expressed as A by B were called as irrational numbers. And firstly, the square root of all the non-perfect squares were found to be irrational. But there are some more numbers which were irrational. For example, consider pi. What is pi? Pi is the ratio of the circumference to diameter of any circle. The circumference to diameter ratio of circles, all circles whether small or big, were found to be the same, and that was equal to pi, isn't it? So the ratio of circumference by diameter was consistent, and this was called pi, and this was found to be an irrational number. You may wonder that you use pi as 22 by 7 and while working out your problems, but let me tell you, pi has been approximated to 22 by 7. It is actually, it cannot be written as a ratio of two integers, but for calculation purposes we have approximated it to 22 by 7. And of course there are more numbers which are irrational. One is, for example, e, which you would be learning about later. It's a constant used for exponential growth of something. E is a constant used for exponential growth, and we will study about all these later, but this is just to tell you that there are numbers which are irrational. There are many numbers which are irrational also, just like there are many rational numbers. But one thing is very clear, both rational and irrational numbers, both of them fall under the real number system. They fall under the real number category, the real number system, and all of them, I mean both of them, can be denoted in the number line, in the real number line. We can plot them. We can find the points in the real number line. We can plot them in the real number line, which we will show you in this same channel later on. You will learn to plot both rational numbers and irrational numbers in the real number line. And I hope you have understood so far. Just that I reiterate on one point. All the other numbers except irrational numbers are rational numbers, just whole numbers, natural numbers, integers, all of them are rational numbers. But irrational numbers are standalone numbers, but both of them fall under the real number category. So thank you.